Okay, so I put this code on AutoClass during the break. At the top of the class page on AutoClass, there is this read network.java, the code we have written in class today, which is able to read the pathway commons simple interaction format file, or maybe it's simple interchange format. I think it's interaction format. So it reads that and computes the average degree, and the important thing is that it reads the network into an adjacency list representation. And you can do with a simple loop like this, you can do different analysis on those, and you can actually implement the techniques that we are going to see next, the clustering and random walks on graphs, these algorithms that I'm going to describe. You can easily implement them on this adjacency list representation that we have seen. So we spent like an entire hour on this simple code, but I think it's worthwhile. If you understand this, it will give you a really good starting point to implement the algorithms that you're going to see later. All right, so we start with clustering, and I'm going to talk about one method in detail, which is MCODE, molecular complex detection, which appeared in BMC Bioinformatics quite a while ago, but it's still, the main reason I'm talking about is it contains some basic graph-centric topological measurements that it uses those to find in a very good, nice, greedy heuristic. It finds clusters in the graph. So it's called MCODE. We will see concepts like K-core and clustering coefficient. So it uses a measure which combines, which integrates clustering coefficient with the K-core coefficient. Okay, so we are going to see these graph centrality measures, clustering coefficient, and MCODE, which is molecular complex detection. You can find the paper in open access, as open access in BMC Bioinformatics. And as I said, it's like maybe from 2000s or something, MCODE, but it's been cited a lot. MCODE, molecular complex detection. It's 2003. An automated method for finding molecular complexes in large protein interaction networks. So just like our in-complex with type of edges, that's a protein interaction network. And how do you find automatically molecular complexes? What's a molecular complex? A molecular complex is a part of the network in which we have stable interactions. They form stable interactions, and it's like finding a community, finding a dense subgraph. Our goal in terms of graph theoretic terms, our goal will be to find out dense subgraphs in these networks. Okay, so if you, for example, take a look at the figures, so these are the algorithms that are here. I'm going to go into detail of these things. For example, if you look at this, this is like a molecular complex, in which many of the nodes here are forming a dense subgraph within themselves. So we have to include these genes in our molecular complex. They may form a molecular complex. So there are different analyses here. Let me see whether, yeah, this is another example. The second highest ranked MCODE predicted complex is involved in RNA processing and modification. So this is a large community of nodes. As you can see, it's really dense compared to the sparse. This subgraph is not that sparse. There are many edges between only like 15 nodes. So our goal will be to find like these dense clusters within the network. So this is another example. Yeah, there are other examples of our goal. These are just subgraphs that exist in this large sparse network. Our goal will be to find those. LSM complex, cleavage polynodulation complex, Saga complex, they're all integrated with each other. Examining complex connectivity with MCODE, you can also do that. All right, so what is this MCODE and how it uses K-core and clustering coefficient? Let's first start. So example algorithm MCODE, as I said, we are going to discuss that. And this graph clustering, finding these dense components, depending on the type of your network. If you have a protein interaction network, physical interactions, the dense cluster may be related to protein complexes. If you're looking for an indirected network like string, where proteins that are involved in the same biological process are also sharing edges between them, you can also find biological pathways by finding these dense clusters. So the problem given to us is, given a protein interaction network, find this term strongly connected component actually is not used correctly here. Strongly connected component is a graph theoretic term which is defined on directed networks. What I want to say here is not strongly, it's densely connected subgraphs. Okay, strongly connected component is a graph theoretic term on directed graphs in which it's a subgraph if there's a path from every node in that subgraph to every other node in that subgraph, then that subgraph is a strongly connected component. Okay, so that's the original true definition of being strongly connected. Here our goal is to find, we are given undirected networks, and our goal is to find densely connected components. The most stringent version of this, which is the clique finding problem, when I say most stringent version, if, for example, your goal is to find a subnetwork, a subgraph in this network in which all of the edges between all pairs of these nodes exist, okay? Which means that if you're looking for a complete graph, all the edges between all of them exist in this graph. For example, imagine all the edges exist between all pairs. I'm not going to draw all of them, but you get the idea. This is called a clique or a complete graph. And finding the largest clique on a graph is an MP complete problem. So it's called the max clique problem. You're not going to be interested in this max clique because even if in max clique, when I say most stringent version, it requires all of the edges between all the pairs to be present. Even if one of the edges is not there, okay, if one of these edges, for example, like this, it's not there, it doesn't mean that it's unimportant biologically. So we're not looking for exact cliques, but we loosen that definition. We make it less stringent. Instead of the requirement of all the edges present, we say we're not just looking at dense. Okay, the density maybe 80%. You may have some thresholds to deem them as connected or dense components, but it's a more loose definition of this clique. Our goal will be to find those. And there are many algorithms. One of my favorites, so MCODE is not one of my favorite algorithms actually that I'm going to describe, but MCODE is, I chose it to show you how such an algorithm, a heuristic, can work to find those communities in graphs. One of my favorite algorithms is this MCL, Markov clustering. It's very efficient, works very large, fast on very large graphs, and it involves taking the powers of the adjacency matrix iteratively to make connections between in dense groups. The connections are going to get stronger, weak connections are going to get weaker, and at some point you're going to have a graph in which the connected components in the graphs will reveal your clusters. Okay, but the main idea is to have powers of your adjacency matrix, taking iteratively taking powers of your adjacency matrix, reveal certain things in the graph. There are other methods, the restricted neighborhood search clustering, super-parametric clustering, these different methods, and we're going to talk in detail about MCODE, molecular complex detection. So I already talked about MCL, so it's takes successive powers of the adjacency matrix. I'm skipping these. You're not responsible for the details of this. You don't need to memorize this RNSC or SPC. Now let's talk about MCODE. Okay. Now, first it starts by taking some measurements for each node in the graph. So if your goal is to figure out, if you have a very large graph and your goal is to find dense subgraphs in this network, if these are like dense subgraphs, first of all, in order to be in a dense subgraph, a single node in this graph has to have a lot of connections. I mean, its neighborhoods should be dense, right? In order to be a member of such a dense community. I mean, you cannot claim, for example, if it was the Facebook social network, you cannot claim to be in a dense community if you only have one friend. Okay, I mean you're in a dense community with only your friend, two friends, but it's not a large community, just two, and it's not even considered a community probably with just two nodes. Therefore, the first thing it starts with is by observing this. It says, let's use this graph theoretic measure to indicate. So clustering coefficient actually is a graph theoretic measure which shows how connected your neighbors are, the neighbors of a vertex are. So it's computed like this. Imagine we have a node and it has some neighbors. Okay, so this is a node V, a vertex. It has, for example, let's label them 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it has 9 neighbors. Clustering coefficient is a measure of how these 9 neighbors are connected with themselves. Okay, it's basically asking, do your friends know each other as well? Okay, that's called clustering coefficient, and it's computed for a node. So clustering coefficient of a node. Every node, if we have not 10,000 nodes in our graph, every one of them will have a different clustering coefficient. Sometimes you may see this term to be used for the entire graph. Usually that means that it's the average clustering coefficient. Okay, but the clustering coefficient is a term that is defined for a vertex of a graph. And as I said, it's a measure which is between 0 and 1. If it's 1, it means all of your neighbors know each other. If it's 0, it means none of your neighbors know each other. Okay? Now, if, for example, my neighborhood is like this, now what I'm going to do is I'm going to change the color, and I'm going to indicate the edges between my neighbors. If none of the edges between my neighbors, the neighbors of V present here, as it's like this, the clustering coefficient will be 0. If, for example, there is one edge between, for example, if 6 and 9 knows each other, if they're connected to each other, there will be an edge between them. Now, what is the clustering coefficient of V? So since it's going to be a measure between 0 and 1, what I need to do is, it's actually a ratio. Clustering coefficient of this vertex V is actually the ratio of the number of edges between your neighbors to the total number of edges that is possible between your neighbors. So what is the total number of edges, undirected edges? Again, we are talking about an undirected network from now on. Okay, what is the total number of edges that is possible between these 9 nodes? Can you tell me? Write in the chat box how many edges there could be. What is the largest number of edges, largest number of red line segments I could draw between my neighbors? I will wait like for 10 or 20 seconds. Any answers? Exactly. So both of them correct. So it's basically the number of neighbors. If the number of neighbors is n, it's n choose 2. Okay, all the possible 2 combinations of n, which is n times n minus 1 divided by 2. Okay, and in this case, it's 9 is n, so 9 times 8 divided by 2, 72 divided by 2, 36. So both of the answers are correct. So there 36 edges are possible for this particular vertex, and if I have only one of those 36 possible edges present, its clustering coefficient becomes 1 over 36. Okay, the largest it could be is where its neighbors are cliques. The common mistakes students make when computing clustering coefficient is to count these edges as well between v and 5 or v and 6 when computing the clustering coefficient. That's an error. These edges actually are there to define one as a neighbor. Okay, in order to want to be a neighbor of v, this edge has to exist there for sure. Okay, so therefore we don't count these edges. The black edges are not counted. The clustering coefficient only considers the edges between the neighbors, for example, like this, and 1, 2, 3, 4, 5, 6. If there are 6 edges present, then it will be 6 divided by 36. It's going to be 1 over 6, the clustering coefficient. The more your neighborhood is connected, the larger your clustering coefficient is. So their main idea was to start with nodes to compute the clustering coefficient for all of the neighbors. Okay, so how do I compute the clustering coefficient? For example, let's go here. How do I compute the clustering coefficient for P1 here? Let's compute, for example, if I want to have system out println clustering coefficient of coefficient of P1 is, now I'm going to write a formula here, which is what? Which is really easy actually, right? Which is this, let's actually get this neighbors.size. If I have int d is equal to neighbors.size, it's going to be d divided by, okay, that's my the number of neighbors. Oh, no, it's not d divided by. I cannot do it like this. Okay, so this d times d minus 1 divided by 2 is the total number of edges I could get the largest. Now, in order to figure out the n, I need to go over all of my neighbors one by one and see whether they're connected. Okay, so how are you going to do that? So let's try to compute the clustering coefficient. So what I need to do is I need to have another enumeration here to go over my neighbors, and I need to maybe go maybe like this n1. Actually, I need to have yeah, I need to have a double for loop like this here. So let me do this. So not a matrix keys, so it's the, I have the neighbors. These are my neighbors now. N1 is a list of my neighbors. For each of my neighbors in N1, okay, so I'm going to say N1 string here is N1 dot next element, and I will also, so let's get this one underneath here. I will do something like this. I will have n. Oh, I was already using n for something else. So for example, let's call it NE, okay? NE divided by this number. NE will be the total number of edges between my neighbors, and this is the maximum number of edges there could be between my D neighbors. Okay, now I'm going to compute NE here. Int NE is equal to 0. I'm going to count how many of my neighbors have edges between them, and I will have to divide this NE by 2 here. I will tell you that later, because between every two neighbors, neighbor 1 and neighbor 2, I will be counting, if they're connected to each other, I will be counting inside this two double for loops, nested for loops. I will be counting that edge twice. Therefore, I need to, if I want to count them exactly once, I need to divide this number by 2. All right, so what I do is I get my neighbor's name, and I will have to get its neighbor list from the adjacency matrix. So it may get a little bit complicated here, but for example, it's let me neighbors of n1 is equal to, I need to get n1s's neighbors from here. Now what I will do is I will have that neighbor list. I have to go over the neighbors of the original one, or neighbors of P1 again, okay, in the second for loop, and check whether this neighbors of N1 contains, so if neighbors of N1 contains key, it's not complex, so let's get the string here too, and 2s, which is n2 dot next element, okay, and sorry, this is going to be n2s. If neighbors of n1 contains key n2s, what does this mean? At this point in this if condition, I have found myself two of my neighbors, n1s and n2s, which are connected to each other. If n2s is contained in the adjacency list of my neighbor n1, okay, then I need to increment any plus plus, okay. So this should do it. So what I just did was in this, so I will also upload this updated version on OptiClass too, but if I didn't make any mistakes, what I just did was for every protein P1, I get its neighbors, and I looked at every pair of its neighbors, and looking at every pair of its neighbors is accomplished by these two loops. So first of all, I go over every one of the neighbors one by one, which I call neighbor 1. I get its string ID from this enumeration, and then for every one of those neighbors, I look at their neighborhood list to see whether one of my other neighbors is in that list too. So which means that I'm looking at two of my neighbors and checking whether there's an edge between them. If there is an edge between them, so this if condition checks whether there's an edge between n1 and n2, I increment this. Since two of my neighbors are going to interchangeably be n1 and n2 separately, and therefore I will be counting each edge between my neighbors twice, so I have to divide it by 2 to get the exact number of my neighbors. And at the end, if I divide this number by the total number of possible connections between my D neighbors, this is D choose 2, I wrote here D choose 2, NE divided by D choose 2 gives me the clustering coefficient. So if we run this again, we will get a lot of lines. We will get 10,000 lines output for each protein. Oh, let's see. Oh, division by 0. So why is okay? So there's something happened here, which is the certain genes here have no neighbors. Okay, So let's see. Oh, by the way, it may be 0 here because if it's an integer division, it's always be an integer division. They are integer numbers, right? D is integer, N is integer. I will have to make one of them float. So make this one float so that it's not going to be 0 anymore. Oh, by the way, this one too. No, this is not going to be 0. This is going to be 0 only when D is. Oh yeah. For example, for a node with just one neighbor, we had these 1 degree nodes, right? For example, look at this. If the vertex V is something like this, it has just one neighbor. The clustering coefficient is undefined for such a neighbor, right? I mean, can you have 1 choose 2? I have one neighbor. If this is V, this is its neighbor. 1 choose 2 is undefined. We cannot have 1 choose 2. I mean, there's no other neighbor considered. What we can do here is that we can do this process, compute the clustering coefficient only for nodes if D is greater than 1. Okay, if you write D is greater than 1 and put the entire thing here within this if statement, compute the clustering coefficient only for nodes with at least 2 neighbors. If you have 2 neighbors and if they're connected, your clustering coefficient is 1, otherwise it's 0. But for a protein with 1 neighbor that I showed here, clustering coefficient is undefined. And therefore, you may choose to have, for example, for such nodes with only 1 neighbor, I may just give clustering coefficient 0 for them. Okay. For example, I can write here as the else statement here. Oh, by the way, the else is going to be not for this one here. Else, I can write, for example, let me just copy this. Else, the clustering coefficient of this one is 0 because it has only 1 neighbor. I can write it like this for 1 neighbor. Once I will print some special message. I can also have 0 clustering coefficient for some other nodes, even if they have 3 neighbors or 4 neighbors. If those 4 neighbors are not connected to each other, they will also have 0 clustering coefficient, but it will be due to because their neighbors are not connected. So I can distinguish between these 2 cases. So let me compile it again and hopefully run this time with no runtime error. Yeah, we had another runtime error, which is, so there is a runtime error here. Let's see how can this happen. It can happen when one protein. Okay, it can happen like this. I know why we had this runtime error. Does anybody have any hint? I actually know that. It's because of the directed nature of the network. Because of a directed, so what may happen is this. Because of in our network we have directed edges, right? So what may happen is that, and it's exactly that case with this protein RFX-ENG. I will actually get rid of this runtime error if I just make my neighbor my network an undirected network. Okay, I will do that because MCODE method works on undirected networks, but because of the direction, the reason for the runtime error was this. Imagine we have a protein P1 here. This is a protein P2. Now, what I did was I assumed that when P1 is connected to P2, P2 is also connected to P1, right? This is how I counted the number of edges. But it may be the case that there may be 0 degree. Actually, yeah, 0 degree proteins which do not appear in my row list. In my enumeration here, my adjacency list contains only the proteins which have some out degrees, have some neighbors, directions towards the other. But what I'm saying here is that the reason I have this runtime exception is that there is some protein ID in the adjacency list of some protein, for example, which is that RFAX here. This RFAX does not actually appear here on the row list because RFAX does not have any outgoing connection. RFAX appears in my edge list as, for example, something is controlling the expression of RFAX. In that case, RFAX is in the adjacency list as a string, but it doesn't occur here. So what we do here, because this runtime exception happens because what we assumed here is that when we get the neighbors of n1, for example, here n2 is a neighbor of n1, when I ask here whether, for example, RFX1 is my neighbor, so when I ask here, get its neighbors as well. So this one may return null, okay? You can check here, for example, if neighbors of n1 is not null, then do that. But it will also mess your count of any which you divided n2 here, which assume undirected interactions. So in order to simplify this thing, what I will do is, in order to get rid of this runtime error, I'm just going to consider undirected edges in my network. So I'm not going to add into my network. I would not add directed edges. Okay, but or another thing you could do is if you want to have these types of edges, you can add the reverse one. But if I just comment this out, I now have in my network edges in both directions. They are undirected. Now it will work with those assumptions. My program should now work. As you can see, we don't get any runtime error. Okay, so it's going to take it's going to output 10,000 lines. A better way to have those 10,000 lines is to put them into a file. Let's call that output.txt, which you can, which is going to be much faster. Your program, as you can see, it ran in like 5 seconds. It was much faster because printing on screen takes more time than printing on a file. So this is a file with not around, since I removed that control state change of type of edges, this now has this many nodes, 8,500 nodes. There are 8,584 nodes in the network, okay? And these are their clustering coefficient. Some of them, okay, look at this. RND2 has a clustering coefficient of 1. This one is, does that mean that they are really largely in a dense cluster? All of its neighbors know each other? That's the one, actually that's one disadvantage of clustering coefficient. The clustering coefficient itself does not give any information about the size of its neighborhood. I mean, it's just a ratio, okay? This RND2, maybe the clustering coefficient of RND2 may be 1 in these 2 cases. Let me show you 2 cases. This may be RND2, and it may have only 2 neighbors which are connected to each other. Okay, what is the clustering coefficient of RND2 in this case? It's 1.0. And what about this case? Do we know whether RND2 is like this? This may also be RND2 with many neighbors, and all of them may be connected to each other. Okay, all these interactions between them, I'm not going to throw them in a tidy manner, but imagine all of the interactions between them exist like this. Okay, the clustering coefficient in that case also may be 1.0. So what does clustering coefficient do in terms of community detection? Not much. It tells the density of its neighbors, how connected they are, but clustering coefficient itself is not sufficient to distinguish between these 2 cases. We need to have something about the degree. Maybe we can maybe use the degree of RND2 to weigh the clustering coefficient with the degree, multiply the clustering coefficient with degree. We could do that, okay? But what the authors of MCODE used something else. In addition to this clustering coefficient, they used a concept called K-core. K-core of a node is this. Basically, by the way, K-core is not specific to a node. The idea of K-core is this. It's a more generic version of what a clique is. Imagine you have a subgraph of size n, okay? If all the edges between these n nodes were present, if it was a complete subgraph, we would call this an n-1 core, because the minimum number of edges, connections between those is, I mean, all of the nodes in this, there is no central node here. I'm considering all the n nodes here. If all of them are connected to each other, every one of them will have n-1 connections, okay? So if in a subgraph, the maximum degree of each of those nodes, the minimum of those maximum degrees is your core number, is your k, okay? So in other words, in a k-core, every node in a k-core subgraph, every node in that subgraph has at least k connections to the others in that subgraph. Therefore, in a clique, a clique is an n-1 core, because every node in that network has n-1 connections to the other node. So K-core is a more generic description of clique. For example, let me draw you a 3-core with 6 nodes or 7 nodes. Let's have 7 nodes here. 1, 2, 3, 4, 5, 6, and let's have the 7th one here. Now, if all of the nodes in this network have at least 3 connections to the others in the network, for example, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this one has already 3, this one has 3 connections, this one has 2 connections, let's make it like this. This one has 2. Now, if you look at all of them, this one has 4 connections, that's okay. You may have more connections, but the minimum number of connections, each of these sub nodes in this graph is 3. So this becomes a 3-core, okay? If all of the nodes in the network, can we call it, is it a 4-core? No, it's not a 4-core. One of the nodes has a 4. A clique is a subgraph which is a complete graph. All the edges in that subgraph exist, okay? In other words, in this 7-node subgraph, if we have 7 times 6 divided by 2, if we have all the 21 edges present in this graph, it's called a clique or a complete graph, okay? And if it's a clique, for example, if we have all the 21 edges in this graph, what would mean is that it would be a 6-core. Why? Because all of those will be connected to all the other 6 members. Okay, so 6-core here, and clustering coefficient is for a vertex, not for a graph. We are not there is so clustering coefficient is a measure that is a measure for a vertex, but K-core, being K-corners, is about the property of an entire subgraph. Okay, so but you can say the average clustering and also the average clustering coefficient, we don't know that. For example, if this is connected to somebody else, okay, like this, and if you're only interested in these, the clustering coefficient of this may be related to nodes that are not in this subgraph. When we are focusing ourselves on a subgraph, we ignore the edges they have to outside this subgraph. For example, I cannot make this subgraph a 4-core by considering the edges they have to the nodes that are outside this subgraph. Imagine these nodes are connected to some other nodes outside this subgraph, okay? When I'm counting, oh, how many edges they have? Oh, this one has 6, this one has 5. Oh, so it must be a 4 core. No, it's not a 4 core. It's still a 3 core because these edges are not, if you consider this subgraph, this node is connected to 3 other nodes in this subgraph. So this subgraph here is a 3 core. Okay? In order to be a 4 core, it has to be connected, each of them have to be connected to a 4th node within the subgraph. That's what K-core definition is. So if we go take a look at the slide, so this was the clustering coefficient that we have talked about, and this is the definition of a K-core. It's a subgraph where every node is connected to the other nodes in that subgraph with at least K edges. So how do you find a certain K-core in a graph, or finding the largest K-core in a graph? There's an algorithm with worst case n cube complexity. I will mention this, but this is what they do. For each node in the graph, the MCODE developers of MCODE, for each node in the graph, they find out what is the largest K-core they can be a member of. Okay, so although being the K-coreness is a property of the entire subgraph, if, for example, this node is a member of a 3 core, and that's if that's the largest it can attain, if this node here, if a specific node here is a member of a 3 core and it cannot be a member of 4 core or 5 core, we give a value of 3 to its K-coreness value of this node. Okay, and we do this for all of the nodes in the graph. We compute, we find out what is the largest K-core it can be a member of. That becomes the K-core value of that node. And this K-core value multiplied by the clustering coefficient becomes the measure that we want to compute. So it's like instead of scaling the clustering coefficient with the degree directly, they make use of, probably they first tried degree and it didn't work that well, and then they tried to figure out how can we find out whether they're in a dense component. And this K-coreness actually is such kind of a measure that tells you whether you are in a clique-like component or not. I'm in a 3 core component, so it means that I'm in a subgraph in which all of the nodes in that subgraph is connected to 3 other nodes. That's the highest I can be. So the way we can compute the K-coreness or the largest K-core or K-core values for each node in the subgraph is like this. First, you start with, by the way, since we cannot just directly use the degrees, okay? You cannot, this algorithm is not going to work correctly, which is, okay, I have for every node, P1, P2, okay, P3, it goes on like this. I look at their degrees, okay? By just looking at their degree, the size of their adjacency list, if the largest one is the highest degree, for example, we had this, the largest degree in this graph was, so let's go to the end. The largest degree is 894 edges. So there is a node, GMB1, with 894 edges. Does that mean that it is in an 894 core? No. Okay, because in order to be in an 894 core, you have to have a subgraph of at least 895 nodes, and all of the 895 nodes in that subgraph should be connected to the other 894 nodes in that subgraph. So it has to be a very large subgraph with a lot of nodes, all of them connected to each other. So this is not the degree itself does not tell us the K-coreness. So the algorithm is, we have an iterative algorithm which is described on this slide. It works on like this. First, it starts with K is equal to 1. Okay, nodes that can only be members of K core 1. So if the degree of a node, for example, let's look at this one. If you look at the output, the other output, protein with degree, MBPF3, it has only one edge. Can this protein ever be a member of 2 core, 3 core? No. it has only one edge. So by looking at its degree, we can say that it can be a member of a maximum of, I mean, this could also be a member of 894, but it's not certain. That's the maximum K-core it can belong to. So if the maximum K-core it can belong to is 1 for this node, what I can do is I can mark all those edges with 1 degree as their K-core value to be 1, and then I may remove them from my network. I need to remove them from my network because they are also contributing to the degrees of the other nodes. For example, there can be let me try to show something like this. Imagine there's a node with degree 4. The largest it can have is K-core 4. But what if its neighbors does not have any other neighbors? For example, this can be a member of at most 1 core, right? This can be a member of at most 1 core because it has only one neighbor. This can be, so what happens is that the vertex with degree 4, the maximum K-core that it could belong to was 4, but it can never be a member of 4 core actually, because when you erase this one, because it's a member of 1 core, when you erase this one from the network, each time I erase them from the network, its degree reduces. As you can see, at the end we are going to see that, oh, okay, actually it's also going to be just it can also be a member of 1 core. So we need to update the degrees dynamically as we first find out all 1 core proteins. So this algorithm is like this. In the first iteration, at k is equal to 1, you identify the proteins in your network that can be member of maximum 1 cores. If they can be a maximum of 1 cores, then there is no use to keep them in the network if you're looking for 2 cores in the second iteration. So you remove all of them from the network. Removing them from the network is going to decrease, since they will not, their edge counts will not count towards computation of K-cores like this. I mean, they're like, for example, when you're computing the K-core to be 3 here, all these nodes, these degrees, 1, 1, they don't contribute towards the K-core count of this one. So that's why they are removed. So when we come to 2, when all such nodes are removed from the network, and there are no nodes that are left with degree 1, what will happen is that in my network, all of the nodes will have at least 2 connections to every one other node. So I will now have at least 2 core network. Now, if a node does not have, then I make my K2, and I remove all the nodes in the network with degrees equal to 2, because they can never be member of a network which is larger than 2. All right, so I keep that iteratively, and at some point, for example, when k is equal to 10, you will only have nodes in the network with at least 10. Every one of the nodes in your network will have degree of 10 at least. So by doing this, until no nodes are left in the network, you will, at the time of removal of a node from the network, you assign its K-core value to be that iteration number, okay? Because when k is equal to 10, it may be a member of 10, and if you didn't remove it, it's connected to at least 10. All the other nodes in that network is at least a member of 10 K-core. So at the time of removal of that node with degree 10, you mark that K-core value to be 10. All right, so that's how we compute the K-core. And here is another example. This subgraph is a 2-core. Every node in this 4-node subgraph is connected to have 2 edges. This is a member of 1 core. This is 0 core. We don't have such singleton nodes in our undirected graph. And this is a 3-core here. So if you look at this subgraph, every node in this subgraph is connected to 3 other within this subgraph. Okay, so this is important. We're just focusing, although this one has, for example, 5 edges, 1, 2, 3, 4, 5. These 2 edges do not count because these 2 nodes are part of the 2-core. After we compute the K-core, the core clustering coefficient is just a multiplication of k-core value and clustering coefficient, and the algorithm just uses these values. They rank the whole proteins in the network with these values and start by the highest k-core protein as a seed and look at its neighborhood and add its neighbors one by one to form a cluster around it. So I'm going to continue, since we're out of time, I'm going to stop here and I'm going to continue with this very, very small left in this algorithm, okay? So actually the algorithm stops here, but I will talk about how the k-core clustering coefficient is used by MCODE to find clusters, to find densely connected clusters in the network. But in terms of methodology, all you need to know from MCODE is the definition of k-core, the definition of clustering coefficient, and how we compute them. All right, and after that on Thursday, I'm going to talk about random walks on graphs in 1 hour, and this will conclude our discussion on biological network analysis. All right, that's it from me for today. Your assignment is going to be similar to computing this clustering coefficient or finding k-cores in the graph, but yeah, let's see. It may even be, I think it may be, how do you finding the largest k-core so it's maybe the implementation of this algorithm. I can give this as your assignment, implement this algorithm that I just described, and it will not be very difficult to have this hash table representation. All you need to do is go over in an enumeration like this, go over the elements, and for example, when k is equal to 1, remove all from this A matrix, you may removal of keys from your A matrix with just adjacency list size 1 is very simple. While you're removing them, you need to go over all the adjacency list again to remove them from their neighbors list as well. So this algorithm can be implemented easily by a similar double for loop like this. And yeah, exactly. And you don't need to use this Java, although it's written in Java. I mean, it's an imperative. You can port this to C, C++, Python. So you will be able to use any language. You will be able to use dictionaries in Python. So whatever language you feel most comfortable with, you will be able to implement your assignment on that language, using that language. All right. So I will also get this latest version of this code on Opticlass. With MCODE right now, at the moment, we found the core clustering coefficient exactly. But the algorithm, which I'm going to continue talking about on Thursday, uses this core clustering coefficient as a way to find the clusters too. Right now, at this moment, we only found core clustering coefficient for all of the vertices in our graph. What we will do is we will sort these vertices in descending order based on their core clustering coefficients, okay? And we will start with the highest core clustering coefficient vertex. And we will look at its neighbors, saying that do they have also core clustering coefficient within certain percentage of this highest one? If it is so, it means that, it also thinks that it's in a high dense neighborhood. We will insert it into its community. So we are going to build a community around the seed vertex by inserting these other neighbors who also have large core clustering coefficient. They will not have as large as the one that as the seed, but for example, get to the clique, get to the community, all the neighbors with for example, within 80% of the core clustering coefficient of the seed. This is what we will do to grow a cluster around the core cluster, around the seed vertex. So that's how the algorithm works, the MCODE algorithm. I will repeat this again at the beginning of the method that I just repeated in a couple of minutes. I will repeat it again at the beginning of Thursday's lecture. And let me stop recording now.